Okay, sounds good. So the next talk is Rachel Lynde. She's a professor at the University of Washington. Also done a great amount of work on program obfuscation, and she'll tell us about recent advances.
Okay, thank you very much. It's an interesting experience to present over the internet. Okay, so we'll start. And the talk I prepared relatively, okay, technically, so we're gonna go through and I will try to monitor Q&A if I figure out how to.
So I'll do it, and if there are questions, I'll I'll interrupt you.
Okay, great. Okay, that's more convenient. Yeah. All right. So, um, thanks very much to Shweta's introduction. So now I can go a little bit faster in the introduction part. Yeah. So the goal here is program obfuscation, and we would like to be able to efficiently transform a program that may contain a lot of valuable information into another one that is functionally equivalent, that compute the same function, and now becomes unintelligible. And this transformation is what we call the obfuscator and is what we're interested in building. And obviously we want this obfuscator to be efficient in the size of the original program and produce an obfuscated program that is polynomially larger. There has been a lot of effort in formalizing what kind of security or what does this unintelligible word mean. And here we focus on a weak version of it. It's called indistinguishability obfuscation. And what it requires is that if we had started with two programs that really compute the same function, however implemented in very different ways, then we would like to transform the programs to look indistinguishable, hard to tell apart. So in other words, that what IO guarantee is that it will hide any implementation difference for the same function. And at a first glance, it appears to be somewhat of a weaker guarantee and isn't what one would intuitively want from a obfuscated program. But the upside is that because the security guarantee is weaker, there's no general impossibility. So we can potentially build IO for all polynomial-sized circuits. And it turns out that even though it appears weaker, it's actually not actually weaker. It's actually a very, very powerful tool in cryptography. So far, there has been a lot of work trying to construct IO. Very briefly, most of them are built on some sort of multilinear map. And you can think of them as a generalization to a bilinear map, but it allows for higher degree pairing. So the first generation all rely on multilinear map with very high degree pairing. And since then, there has been a lot of work trying to kind of reduce the degree needed. And in the second generation, where we reduce the degree needed using randomized encoding, and we can manage to drive the degree all the way down to degree 3. In other words, just needing trilinear map. A very, very important tool that started to appear is the use of PRG with some simple structure. And in this second generation, the simple structure we want is the locality of the PRG. More recently, that using a different type of approach, using homomorphic encryption, we managed to actually rely on only bilinear map with just degree 2. And here, we need a different type of simple PRG, and which we call a low degree noise generator that I will going to detail very quickly, and also together with LWE. So this third generation of using homomorphic encryption is what I am going to focus on in this talk. And in the most recent work, we actually managed to show that the low degree noise generator is the only simple PRG, simple sort of pseudo randomness generator that we need. Okay, so since all the other primitives like bilinear map and LWE, you're probably very familiar with, so let me just dive right into this low degree noise generator. What is it? What properties we want? A noise generator is an expanding function over ZP. So it's an arithmetic function. We would like to expand a seed that is of length n into an output r that is polynomially longer. Think about it as n to the 1.01 any n to the 1 plus epsilon is enough. We would like to have really small degree, minimal degree possible over ZP, but we also want some structure. One structure is that we would like the output to be small. Here by small, I literally mean polynomially bounded, as opposed to say smaller comparing with the modulus P. And the reason that we want this output to be small will become later in the talk, and this is because of constraint in pairing groups. In order to do discrete logarithm by force, we would like the output to be polynomially small. So given that the output is small, we need to think about what kind of security property we have from such small outputs. Instead of asking for the outputs to be pseudo-random, all we need is some hiding property. Intuitively, it means that this output R can hide even smaller noise E, upper bounded by some bound B. And R should reasonably, naturally be larger than B, but still polynomially sized. More precisely, we would like to say that when R is added with this noise E, which is smaller, then I would like the, if I look at each of the coordinates, say Ri plus Ei, these two distribution, which is Ri without adding Ei versus adding Ei, should be close to each other. And this is one way to formalize what it means for R plus E to hide E. For some of you, you might already be thinking, wait a second, right?
Right.
It's very, yeah.
One question. So you want the Ri plus Ei to simultaneously, it's sort of it's not a coordinate-wise kind of indistinguishability. You really want all the Ri plus Ei to look like Ri, I suppose.
Yes, exactly. I really want all the Ri plus Ei to look like R. So,
Okay.
more accurately, I should rather say that the distribution of R plus E and the distribution of R are close.
Yeah, right.
But I cannot illustrate high dimensions, so in the slide, we only talk about one coordinate. Yeah, but that's a very good point. It's a bit confusing. Okay, so for some of you that you might already be thinking that, wait a second, if our I's are polynomially small, there's no way that it can really hide an EI, even if EI is just 0 or 1. Okay, this is for people working with lattices, we all know that the smudge noise needs to be super polynomially large in order to completely hide a noise. So therefore, we cannot hope that R plus E completely hides E, and at the best, we can hope that it partially hides E. What does partially mean? This is a very good question, and in the literature, we have had two different formalizations. One is called pseudo-float smudging, the other is called perturbation resilience. And let me give you the definition for perturbation resilience. What this requires is that these two distributions do not need to be negligibly close, but rather we just want the distinguishing advantage to be bounded away from 1. So as you can see that we actually allow quite a relaxed margin, that we know that distinguishing advantage is at least some inverse polynomial, but we only require it to be smaller than 1 minus some inverse polynomial. Okay. So this is what we want. We want the output of the noise generator to be small, and we want them to have partial hiding property. So now the next crucial question is how low degree these generators can be. We know that degree 1 is impossible because we can solve linear system using Gaussian elimination. So therefore, what about the degree 2? Unfortunately, so far we have no candidate with degree 2. A very natural attempt everybody would want to try is to take some random degree 2 multivariate polynomial. Here I write them as a system, as a sum of quadratic monomials. And in order to make sure that the output is small, we will evaluate those polynomials over the reals so that it does not create cancellation mod P. Because once it creates cancellation, we have no way of controlling the output of being small. And to make sure that it does not create cancellation, we'll choose all the coefficients of each of the monomial together with the input from some small distribution. You can think about it as small Gaussian or small uniform. This will guarantee that the output is also small and much smaller than the modulus, and therefore there's no cancellation. Unfortunately, exactly because of the fact that there's no cancellation, this kind of degree 2 real polynomials can be attacked using sum of square attacks. So, so this seems to suggest that the minimal degree needs to be 3. Okay? And indeed, if we have a random degree 3 polynomial, they can be shown to be resistant to sum of square attacks. But we're greedy, we don't want degree 3, so we managed to get degree 2.5. What is degree 2.5? I'm not inventing new math, but let me just explain. So we will indeed start with a degree 3 multivariate polynomial, and now we want to somehow compress down its degree over ZP. How? By hiding one of those input vector U as LWE noise. Okay? So hiding it as LWE noise means that we're creating these LWE samples of the form A S prime plus U, and U is exactly used as LWE noise. So if I write it just as a rewriting of the equations, we know that U equals to C times S, where S is minus S prime comma 1. Nothing has happened so far, and let's see that how we can compute this degree 3 polynomial G now. Because U equals to CS, I can do a change of variable. And now, can you see my cursor? Okay, looks good, yeah. I can do a change of variable. Now, this function G, I can rewrite it as a different polynomial, which acts on C and also on V tensor S, comma W. The nice part is that I can view this C, which is LW sample, as something in the public, and we call it the public seed of this noise generator. And the rest that must be hidden is what we call the private seed. Now, if you look at what is the degree of the noise generator, technically it's still degree 3 over the public seed and the private seed. However, we see that the degree on the private seed now is only 2. And the degree on the public seed is 1. And this is what we mean by degree 2.5. Because ultimately what we care about is the degree on the private part.
So Rachel, this you could have done anyway by just kind of, you're pre-processing a bunch of variables, so you're increasing the number of variables. So this you could have done, you know, you can do it with any polynomial, right? So
I can do it with any polynomial. Indeed, I can generalize to any degree polynomial. Actually, there is a limit. I can only generalize to a constant degree polynomial. So to summarize so far, what we get is this degree 2.5 noise generator, where the degree on the private seed is 2. And the 0.5 part sort of signals the computation on the public part. So the security we want, as we said, is that given the LWE samples, we would like the output of the polynomial, which is R, plus E to partially hide E. And this assumption can be further decomposed into 2 assumptions, which is just to help us to understand what this assumption is asking for. The first necessary part is that we want the random degree 3 polynomial to have this partial hiding property if there's without those additional LWE samples that encodes the first vector U. Okay, so in other words, I just want the output of G degree 3 polynomial G plus E to partially hide E. And this we can actually show that is resistant to SOS attacks because of the degree. And the next assumption is that how does the LWE sample come into play? We would like to make sure that given the LWE samples encoding the first vector U, in some sense that because of LWE, this U is hidden. Okay? So the assumption that I give you LWE sample with a consistent U used in the evaluation of the polynomial is indistinguishable from I give you LWE sample with an independent U prime. So if we put those 2 assumptions together, it will naturally imply the partial hiding property.
So Rachel,
Yeah,
this polynomial, this degree 2.5 polynomial is now not over the rails. It's a mod p polynomial, right?
it's a mod p polynomial, exactly.
Indeed, if it were a polynomial over the rails, you would be able to break it essentially, because the number of variables is too few. Is that right? Or
If it's a degree 2 polynomial, then and it's over the reals, then SOS attack would again come to play.
right,
However, with this change of variable, to make it into degree 2, essentially we did a change of variable. And with this change of variable, they introduced the cancellation, and that's why it's not clear anymore that whether SOS would apply.
right. So there's one more question in the Q&A. If you press the button at the bottom, you
Yeah.
see. Okay.
Without reaching for LW-based things, would reducing the degree using relinearization-based technique work? This seems somewhat similar. Okay, so relinearization is something that we always need to be careful about. What happens here is that we still have sort of, even if you count the number of variables in the private seed alone, there's actually roughly n variables, and the number of outputs is n to the 1.01. So you cannot directly relinearize because there is still too many variables. I hope this answers the question. Okay, so we're gonna continue. So as Vinod has observed that there's nothing special about degree 3, we can actually generalize to degree constant polynomials. But for the purpose of this talk, we can just think about the degree 3 version. So the theorem that we have now is that we can actually build IO using bilinear map LWE together with such degree 2.5 noise generator. More accurately, we actually use the tools to build the functional encryption for P directly, which as previous work has shown is more or less equivalent to IO up to some security loss. Just to mention again that previous works will also need to rely on block local PRGs in this theorem, and the latest work got rid of it. So there are two important tools in this theorem. One is what we call special homomorphic encoding, and the other is what we call partially hiding functional encryption, that I will introduce them in the rest of the talk. Okay, so let's now start to see how this theorem is proven. We said that the goal that we want to build is a functional encryption, which also gives you IO. And roughly what functional encryption allows us to do is to give out the ciphertext for inputs and give out the partial functional secret key for functions. And the decryption will reveal exactly the output of the function evaluated on the encrypted input. And the privacy guarantee is that only these outputs are revealed. The magic of functional encryption, why it's so powerful, is because that you can give out any number of ciphertexts and any number of function secret key for different functions and derive all the possible combination of outputs for different f and x, and the privacy still guarantees that it will reveal only these different combination of outputs. Since we are at functional encryption, and one of the important tools we look at is what we call partially hiding functional encryption. Let me just give you this tell you what this primitive is right away. So partially hiding functional encryption adds a public input to the ciphertext. Now the ciphertext is created encoding a private input X and a public input A. And the rest is more or less the same. We would like the correctness to reveal both the output, but also the public input. And the privacy guarantee should mean that only this information are revealed. So the only difference between partial hiding functional encryption and the classical functional encryption is the presence of some public, wait, what happened? Is the presence of the public input. So one question is why do we formalize this? And the reason that we can see is that it is very useful for evaluating this degree 2.5 noise generator. whose seed contains the public part and the private part. And the nice part is that because we do not require hiding of the public input, we can actually handle those functions that compute up to NC1 computation on the public input. And whereas in the functional encryption world where everything needs to be hidden, we're still getting functional encryption for NC1 is still a very hard task and precisely the task that we're dealing with now. Okay, so keep these two in mind. Let's come back to the task of constructing I/O. It turns out that for constructing I/O, we just need a weaker variant of this functional encryption, which we will only ever give out a single secret key. But you need to think about this secret key as producing, as encoding a function that has a very long output instead of a single output. And here, obviously, we will still allow lots of different ciphertexts for different inputs, and privacy make sure that only the right output is revealed. So one more requirement in order to get I/O is that we will need to make sure that the size of the ciphertext, which usually we think about as a polynomial in the length of the input, and here we would like the size of the ciphertext to be to allow it to also scale somewhat with the size of the function, but as long as it's not linearly scaling, instead it is sublinear in the size of the function. And this is what we call the compactness requirement. So for the rest of the talk, we're going to try to construct this single key functional encryption with compactness. And most of the time, you can ignore the fact that there are lots of different ciphertexts, and we can just think about single ciphertext. And I will not explicitly address compactness, but the construction is compact, pretty easy to observe. Okay. All right, so our starting point is the similarity and the difference between functional encryption and homomorphic encryption. Well, homomorphic encryption can also allow us to do computation on some encrypted input, and it produces a ciphertext of the output. We're going to call this output ciphertext HCTF. The difference is that here, homomorphic encryption, it really reveals no information about X or about the output Y. Whereas in functional encryption, we actually want to get Y. Therefore, the most important difference if we want to build functional encryption from homomorphic encryption is to decrypt in a private way. So what about trying to decrypt using some simple functional encryption scheme? Right? We're going to use a simple encryption scheme and include in the functional encryption ciphertext of this simple FE scheme, encrypting some input, and in the secret key of the simple FE scheme of some function H, so that when we decrypt it, it will exactly decrypt the output ciphertext HCTF and reveal Y. We would like to make sure that the proper security property of the functional encryption scheme will make sure that only Y is revealed. And this relates to this need for ensuring integrity in the sense that only the right output ciphertext for the legitimate function F for which a secret key has been issued can be decrypted. In addition, that it seems to be somewhat weird that why I'm using a functional encryption scheme to construct a functional encryption scheme. To make sure that this paradigm is not kind of doing nothing, we want to make sure that the function that the simple FE evaluates in order to decrypt should be much simpler than the function F that we are actually computing. When we construct, F is an arbitrary polynomial time function, and H is going to be something much simpler. All right, so let's go ahead and try to figure out what kind of function and input will allow us to do this. Oh, so forgot to say that ideally we want H to be so simple that ultimately we can implement this simple FE using standard assumption. All right, so we want this function encryption to help us to decrypt. So that means that inside it, we wanted to compute the decryption function. So for most of the homomorphic encryption, decryption is basically a linear operation on the secret key and the output ciphertext, followed by a threshold function. The problem is that this is not simple. This is actually an NC1 function because of the threshold. So one first thought is that we want H to be simple. So what about just not doing the threshold? This would correspond to doing only half decryption, which only does the linear computation. And what this linear computation will give us is going to be the output plus the noise. So this brought us a problem, which is that the output plus the noise may be leaking a lot of sensitive information. And indeed, this noise in the output ciphertext can depend on the secret key of the homomorphic encryption as well as the encrypted input. So to help bridge to remedy for the privacy, our next thought is, what about using our noise generator to generate some smudge noise to hide E? Okay. So now we're computing instead on the half decryption plus the noise generation. Now privacy come back again because the noise generator has this partial hiding property that will help us to hide E. And for the purpose of this talk, we were going to ignore the fact that the partial hiding is imperfect, and I will only mention it towards the end. But for now, let's think about it really perfectly hides E. And nice part is that we have not increased the complexity of H by much. Right now, it is just a degree 2.5 function. The next problem we need to solve is the integrity. In fact, in order to decrypt the output ciphertext, it seems that so far, how can this function H take the output ciphertext as the input? Unless we put it actually in the corresponding ciphertext. But at the encryption time, we actually don't know what is F, and we cannot even create this output ciphertext. So to solve the integrity problem, we can use the special homomorphic encoding as a tool or partial hiding functional encryption. And let me tell you about only the solution using special homomorphic encoding here. So what is this special homomorphic encoding? We are all very familiar with homomorphic encryption. It allows us to evaluate the function f homomorphically and get the encryption of the output. The nice part is that it has very simple decryption, nearly linear. We saw that a linear operation will already give us the output perturbed with some noise. The special homomorphic encoding actually has two parts, separates the homomorphic evaluation into two parts. So first, it starts with some public parameter A that is shared in different instances of this homomorphic encoding. And encryption will depend on both the secret key as well as the public parameter. And these parameter A are really just LWE matrices, lots of them. Now, homomorphic evaluation will evaluate on the ciphertext and produce some kind of, we can also call it the ciphertext of the output. But there is also a public evaluation part, which depends only on the public parameter and produces a matrix called AF. And the nice part is that the decryption equation now changed to this form. And the unique thing is that now the secret key does not need to directly operate with the output ciphertext anymore. Instead, the secret key acts together with the public matrix AF, and the computed output subtract with the output ciphertext gives the output plus E. So this seems to be a rather minor change, but if we gaze at it a little bit closely, we'll see its power. So let me call this the output of the linear half linear decryption SF. And we observe that if I add to SF some smudge noise R, what it equals to is with rearranging the equation, the HCTF plus E plus Y plus E plus R. And this right-hand side tells us that really only information conveyed is Y. Why? Because the output ciphertext can be computed publicly. E plus R is now smudged, therefore E is hidden, and hence the only information revealed is Y. In other words, you can really view SF plus R as sort of functional key for F that reveals only the output of F. A catch is here that in order to enable this kind of decryption equation, the public parameter or the LW matrices A are reused everywhere, and hence the secret key must be sampled for each ciphertext freshly. Putting these two together, an alternative view of this special homomorphic encoding is that it's actually one ciphertext functional encryption with a very, very simple key generation. Okay. So with this, we see that now we know what to give to the function H. This function H just need to compute the linear decryption acting on the secret key and AF, which is public, plus the noise generator to produce the Martian noise R. And since the what did it produce give you, since the output ciphertext can be publicly computed, from this output we can recover the output Y. Okay. And now, okay, so this solves our integrity problem. Next, what are those tools that we need and can we have them? Well, one tool that we need is this special homomorphic encryption, and actually we show that we can get special homomorphic encryption with this special decryption equation all the way for RP from LWE. And the other, and previously there has been some construction, but do not handle polynomial or polynomial computation. And the next tool that we need is how to implement this simple functional encryption, which now is evaluating a degree 2.5 function. And this can be computed using exactly our partially hiding functional encryption. And we show that this tool can be implemented using bilinear map, handling up to NC1 public computation and the degree 2 private computation. And one catch with this construction is that the output will be computed in the exponent of the target group. And therefore, if we really want to obtain the output of function H, which is going to be computed in the exponent of the target group, we need to do discrete logarithm by brute force. And to do that, we really need both E plus R to be small in order to make that feasible. And this is why that we want a noise generator to have polynomial-sized, polynomial magnitude output. Vinod, how am I doing in time?
-4 minutes, Rachel. So we should wrap up.
Okay, you didn't stop me, so but okay.
You
so
stopped yourself. So
yeah. Good. Okay, so I think I have already give out the construction, and I had some slides for how to build the special homomorphic encryption. One only thing that I want to say is that it's basically following from predicate encryption. Any existing predicate encryption for P would give us this tool. And we are not going to go through the slides for them. And jumping directly to the concluding slide. What we have seen for now is that this degree 2.5 generator, special homomorphic encryption, and partially hiding functional encryption to build a functional encryption with weak security. Why weak security, which I sort of hide it under the rug, is that this noise generator actually only have partial hiding property. And because of the partial hiding, that it's not complete hiding, it leads to the functional encryption with only weak security. Oh. And in order to get full functional encryption and hence I/O, we will need to do hardness amplification. And this is what Ayush is going to talk about next. And I give you sort of the rough guideline on how to obtain degree 2.5 noise generator, but did not give you a very specific candidate. But in the later talk that Amit is going to talk about what are the concrete candidates and some of the cryptanalysis. And that's it. Thank you.
Rachel, can I ask a quick question? Can
Yes.
you go back? Can you go back a couple of slides?
Which one?
The one where you say that you do this in the exponent. It was just 2 slides ago, I think.
Yeah, here.
Yeah, this theorem here. It says that,
Yeah.
yes, this one. So it says that with outputs, this asterisk, this with outputs in the exponent of the target group. So here, as far as I understand, you can actually decode it, right? I mean, it's polynomially bounded.
Yes, because you can actually compute the output.
You do the mod, right? So you're doing the modulus reduction outside, right?
Reduction here.
Yeah. Okay, that's nice. That's so nice.
So I believe that's in about 8 minutes.
Okay.
You do it with you do it directly without all the structure of FHE. So you kind of they have much more structure around than you did directly, or am I not understanding right?
No, so the structure of the FHE is something that both approaches need. So even in my talk, I described that the theorem was that noisy linear FE plus this kind of special FHE will give IO. So Rachel talked more about the structured FHE. I did not talk about it at all, but it's also something, I mean, both approaches need that.
Okay.
So, Ran, I think that in my talk where you see that this function H, the simple FE is trying to compute, is doing half linear decryption plus the noise generator. So you can sort of view, I understand that there's Shirata's view, and then you can sort of view that as doing a linear computation plus noise. So that sort of fits into what Shirata is saying.